That's Stray's tutoring? Hey guys, welcome to another video where we'll be going over X-ray crystallography. X-ray crystallography is a very interesting type of experimental science that we'll be talking about because we've always wondered, how are we able to see these structures of proteins, these large macromolecules, and piece together how they look? It's because of X-ray crystallography. What is this thing, right? We have two guys at the bottom, right? What is this whole crystallography thing that we speak of? Well, it's a type of experimental science, and it helps us determine the atomic structure and the molecular structure of a crystal. So what we have is, we have some type of crystal that we have, which can be made in a lab or some sort. And when an X-ray light or a beam of light, which would be an X-ray, it hits this crystal, we start to diffract the crystal or the beam that went through that crystal, and it'll go ahead and hit this sort of plane or probe that we have, and a detector will pick that up, and we're able to create some sort of map to map out what exactly is in this crystal. So more specifically, proteins, we'll throw this in the crystal, and that's how we're able to see its atomic structure. This was founded by our guys William and Lawrence Braggs, I believe they are. In this experiment, they found that having an X-ray hit a crystal, it will start diffraction. And diffraction is another fancy way of scattered. So light gets scattered, and then we're able to identify what is the structure of a crystal. And these brainy individuals decided, why don't we just put protein in this crystal? And this is mind-blowing. This is new and innovative, because now we're able to see the structures of proteins like we've never were able to see before. So here's an idea of what an X-ray crystallography looks like, the actual instrument used. And if you notice, all of them have this V shape. So if you ever forget, just remember it has that cool V shape. And even if we forget these schematics and look at the actual picture, it does kind of have that, I would say, like V cut. So if we look more deep into this, and I'll just go ahead and erase, what we have is the X-ray source here, of course. So this is very important because we need that X-ray source to go ahead and create that incident optic or light incident X-rays onto our sample or our crystal, where it may have some sort of protein inside, and we want to know the exact structure. So we have this X-ray source of incident light or incident X-rays. Again, what does that mean? Scatter. So scatter. And then we have a receiving optics, and then a detector, which will detect through light sources that are from this scattering from the sample. And then of course we have this like a disk structure or ganometer. And what this does is it rotates on an axis, allowing for us to see a 3D model. So this light gets hit into this crystal, and it's kind of like a 360 view of what's in that crystal. And again, if you guys look at the other images, it's kind of the same deal here. All these schematics kind of are the same, and of course not all of them are going to look 100% the same, but the overall concept is an X-ray source, and then of course the sample, and then the receiving optics and a detector. So if we go into each phase, of course we have our X-ray, incident X-rays. It hits the crystal, and this causes some diffraction. And this diffraction is picked up by a panel or a diffraction pattern. After this, we have a transformation of these scatterings. And this transformation, if I skip over to the next slide, it transforms the signal into frequency. So after this, it's picked up through an electron density map, And in this map, we can determine the atomic structure or atomic model. If we look down below, we see the next steps, and these are easy ways to memorize. You'll just kind of have our X-ray come in. You have our crystal. Then we have diffraction, or that scattering. And then we can get an electron density map, and then we can go ahead and piece together the protein model. And if we look even closer, we know that diffraction, what's happening is we have an incident X-ray that goes ahead. It doesn't interact directly with the electrons, but what will happen is it'll actually shoot out, and this shooting out causes that, remember, whenever I draw this, think of diffraction, that scatteredness out into the detector, so we can see exactly what is inside of that crystal. And this is all determined through Bragg's law, which will be a separate video. But what I really want to get out of this is that we have an incident X-ray that goes ahead and that not directly interacts with the electrons, but will actually diffract those X-rays out. And then, of course, will be picked up by the detector. And of course, this is all part of the phase 2 that we saw here, where we have the signal being transformed into a frequency. And once we get the frequency, we're able to draw it out into an electron density map. And from the map, of course, we can see what protein is there. Okay, so that was just a quick video about X-ray crystallography, a very brief, short, simple explanation, because there is actual mathematics involved into this. However, we just want to keep it simple, where we have X-rays of incident light that hit a crystal, scatter, they're picked up, translated into a frequency, and then into an electron density map, and then we can go ahead and get our atomic model. All right, guys, so that was just a quick video, and I'll see you guys in the next one. All right, peace.